Hello everyone. So welcome to the course on large language models. This is another new lecture on knowledge editing, model editing. Today's lecture is going to be very special in the sense that this is a new paradigm which started a couple of years back. It's a very ambitious paradigm, I would say, because if this is going to be successful, then this will basically make a huge change in the learning paradigm of language models, deep learning in general. And we will see that some of the concepts that we are going to discuss, these concepts are still new, right? Still experimentally, they are experimentally validated, but still there are ample amount of scopes to improve those concepts, those models. Okay. Unlike let's say transformer architecture and their pre-training fine-tuning parts that we discussed, which are mostly well studied, right? People understood the mechanism, but this part of the LLM is not still very clear. Okay, so I thought this is going to be an interesting part because ultimately since this field is evolving, right, if some of you take this as your research area, right, for next 2-3 years, I think that would be great. So let's get started. But first thing first, today's breaking news is as follows. September 17, Mistral. I love this company because they always build small models, and I told last time also that I'm in favor of building small models. So Mistral built their first multimodal model called Pixtral. This is a 12 billion model. This is their first multimodal model, which consists of a vision encoder with 400 million parameters and and a decoder with 12 billion parameter, right? It has been tested on multiple benchmark, right? Specifically this MMMU benchmark, which is a multimodal reasoning benchmark, right? On this benchmark, it achieves significant performance across different tasks within the benchmark and across different baselines. So you can check out their blog for more understanding of this model, Pixtral. Okay, so let's look at the motivation behind knowledge editing, right? All of us know that these LLM models are trained. They need to be trained periodically, otherwise they'll get outdated, right? For example, the last ChatGPT version, not GPT-4, the one before that, this was trained on datasets till 2021. So if you have any query which are related to, let's say, recent incidents, right, you may not be able to get updated output from large language model, right? So for example, let's say you give this query, right, did Lionel Messi win the FIFA World Cup? And if the model is outdated, it will say that Messi had not won a FIFA World Cup with the Argentina nation team, right? So this is not correct, because we know that in 2022 Argentina won the FIFA World Cup and Messi was the part of the team, right? So now the question is, if you have such an outdated model, not entirely outdated, but let's say some of the facts are outdated, right? How do you update those facts? So this is the question that we are interested in, right, in this specific part of the course. So the easy option would be the kind of knowledge that you basically want to incorporate into the model, right? You collect all those knowledge, right, and you fine tune the model. The simple approach, right? You fine tune the model. Now the question is, now fine tuning is good, but how many times you are going to fine tune, right? You can say that, well, I have this 6 months of time period. Every 6 months I collect all the updated knowledge and I will fine tune the language model with the updated knowledge, right? But fine tuning is always costly, always expensive. This is a statistics. So Llama was trained for 21 days on roughly 2,800 GPUs, right? which costed over more than 2.4 million USD with 1,000 tons of carbon dioxide emitted. This is really costly in terms of money, in terms of equipment, in terms of environment pollution, right? So fine tuning is not a good approach, right? And the second problem with fine tuning is that when you have a set of facts which you want to incorporate, right, and you only fine tune based on these facts, your model may get biased, right? The model may overfit. Okay, so because this kind of fine tuning is unconstrained, where you are not putting any constraint, you are saying that, look, we have this LLM and you have this set of facts, I want to fine tune the LLM based on these facts, I just do a normal fine tuning, kind of task specific fine tuning, right? The model will get biased in the sense that it may forget some of the pretend knowledge, right? We'll see in the later part of the lecture that if you do fine tuning, full fine tuning with this knowledge, with the updated knowledge, you see the model will start forgetting some of the pretend knowledge. Okay, so what's the remedy then? So people started working on knowledge editing. So the idea is that you think of this large language model as some sort of database, right? Some sort of knowledge base where all sorts of knowledge are stored in different parts of the network. We'll discuss which part of the network stores which type of knowledge, right? And you basically edit those knowledge based on the fact that is given to you. And you see, this is very fascinating, because if knowledge editing is really successful, then you do not need to do fine tuning, right? But as I mentioned, the research so far on knowledge editing is not very successful. It's still a very initial stage, because people propose methods, but then there are also drawbacks that others identify. Okay, so when we talk about knowledge, some of you know that in knowledge graph or knowledge base, right, we generally store our factual knowledge or factual information using a triplet like S, R, O, right? S is the subject, R is a relation, and O is the object, right? For example, the Space Needle is located in the city of Seattle, right? The subject is the Space Needle, relation is location, and object is Seattle, right? So in a knowledge graph or a knowledge base, right, you can essentially store this triplet, the Space Needle, location, and Seattle, right? You can think of it as a graph in case of knowledge graph, where nodes are essentially subjects or objects and links are relations, right? And an object can also be a subject for another relation, remember this. But we do not know whether large language model actually stores knowledge in this way, right? Whether LLM has some sort of inbuilt or inherent knowledge graph or knowledge base is not very clear to us. And what is the goal of knowledge editing? The goal of a knowledge editing is that, let's say you are given this fact, right, and you know that when you give this as a prompt, let's say the Space Needle is located in the city of dash, in general the LLM returns Seattle as the output, right? But you want to change it to Goa, right? So you want that the model will output, when you feed this as a prompt, the Space Needle is located in the city of dash, you want the model to return Goa as the output. So your input triplet is S, R, O. This is the default triplet which is assumed to be stored into the memory of large language model, and you want that this will be updated to this S, R, O star. Remember these notations, because we will use these notations throughout the slide, and please remember this. Okay, similarly, let's say the US president, so the US comma president comma Barack Obama, and you want to modify this to update the knowledge of this, and you want the model to return Joe Biden, right, and so on and so forth. Okay, so SRO is the original triplet, and the updated triplet is SRO star. Now this is the goal of knowledge editing, right? Now when you do that, when you edit, let's say you are successful in editing knowledge inside the memory of a model, right? Now this kind of editing will have a lot of effect. Think about the effect. It is not the case that you pinpoint a specific part which represents the knowledge and you just edit it. It is not a database, by the way, right, that you write some SQL query and it will just update the object, right? And remember, all these subject relation objects, these are essentially very fuzzy concepts, because as I mentioned, we do not know whether this kind of relation is at all maintained within the memory of not or not, right? And subject object relations, these are stored in terms of some sort of embeddings, some sort of vectors. Okay, so let's say you are successful in editing the knowledge, right? What are the other effects of this editing? One effect could be that if you are able to edit the query that the US president is Joe Biden, right? Earlier it was Barack Obama, now it is Joe Biden, right? The model should also be able to respond consistently for the paraphrased version of the prompt, right? So your prompt is the US president is dash, and the model returns Joe Biden. If you ask the model in terms of a question that who is the current president of US, right, the model should be able to say that this is Joe Biden, right? So when you paraphrase the prompt, the model should be consistently returning correct or updated knowledge, right? Similarly, think about it. When you edit a knowledge, it may happen that some of the related knowledges, right, can also be updated, right, which should not have been updated, right? So let's say who is the so let's say you updated this fact that who is the current president of United States, and the output is the updated output is Joe Biden. Now if you ask who is the let's say where does current president's office is in the US, you should, I mean, your knowledge, I mean, the language model should be able to say that this is Washington DC, right? It should not say that this is New York. So the related concepts which are related to the US president or Joe Biden should may be affected, may not be affected, depending on the context, right? So based on this effects, we will define three conditions, right? The first condition is called reliability. What is reliability? So if function is essentially the LLM, right? The theta dash is the updated parameter after knowledge editing. So the edited model should select y alt. What is y alt? Y alt is the updated output, right, instead of y old, for a given input triplet t from d sub x, where d sub x is the set of targeted queries. Again, remember this notation, d sub x. So d sub x has all sets of queries which you want to update. Okay, all sets of queries, all sets of knowledge that you want to update, d sub x. So for all d sub x, your model should be able to produce the updated output y alt instead of the old output y old. Okay, this is called reliability. This term is used in different papers in different ways, but concept is the same. The second condition is called generalization. It says that, so we saw what is dx. Dx is a set of knowledge that you want to update, right? Px is a paraphrased version of all those knowledge, right? You can think of Px as a superset of dx. It's a paraphrased version of dx, and you also want the model to return the updated output y alt for all the paraphrased queries Px. For example, if the input is the president of the US is dash, the model should return Joe Biden. If the input is who is the president of the US, it should also return Joe Biden. And these two are the paraphrased version of each other. Okay, so this is called generalization. The third one is called localization. Localization says that the edit should be localized. It should not propagate across the memory of a model. Meaning that, so we discussed what is dx, we discussed what is px. Now we introduce another term which is ox. Ox is all the non-targeted queries, right? So you update the model such that for non-targeted queries it will always return the old output, right? For example, for example, let's say you updated the knowledge of the US president thing. Now if the query is who is the president of Russia is dash, it should say that it is the president is Vladimir Putin. It should not return something else, because this query has nothing to do with dx or px, right? So we expect the model to return the old output for those queries which are not a part of the said dx and px. Okay, so this is called localization. All right, now let's move into the different techniques which have been proposed for model editing, knowledge editing, right? Now think about it. If you are told to edit a large language model, what is going to be your approach? What do you think? What is going to be your approach? The first approach would be that you will attempt to edit the parameters or update the parameters of the model, right, with some constraint, right? So this is called global optimization. In global optimization, the methods which follow global optimization techniques, they basically update the parameters of the model with certain constraints, some sort of constraint optimization problem. The second approach is you think of some additional memories. You have LLM's own memory, which is all these neurons, right? You think of additional memories, right? And you store the updated knowledge into the additional memory. Okay, and whenever a query or a the query related to the updated knowledge is given to the model will look at the memory, right, this additional memory, and that memory will be returned. The output of the memory, or the member of the memory will be returned. Some member of the memory will be returned. Now this is called external memorization. You have some external memory, some sort of cache memory. We'll discuss the cache memory concept here, right? And you store all the updated knowledge into the cache memory. The third approach is more sophisticated. The third approach says that in global optimization, you update the entire memory space of a large language model. In local modification, you identify or pinpoint the neuron which is responsible for this knowledge, and you only update that neuron. This is a localized view of knowledge editing. Okay, so generally if you look at the literature so far, there are plenty of papers, more than 50-60 papers. You can classify this into these three categories based on where you are updating, whether you are updating the entire parameter, right, or the external parameter or the internal parameter, and how you are updating. Is it a direct optimization or a direct incorporation of this update? Based on these two factors, you categorize algorithms into three components. This is a pictorial depiction of the update, okay, the one that I just mentioned. Look at here. So in external memory, what you are doing, so this is your parameters, LLM's parameters, right? And this is the memory that you want to add, right? Some sort of cache memory where the edited knowledge will be stored. So this will be added here. So now your model space, your parameter space has increased. The parameter space consists of the original parameter as well as the original parameter as well as the updated memory, right? In global optimization, what we do, so this is my original parameter, right? In this technique, what we do, we will learn the gradient, change in gradient. Okay, or in other words, if W is the original parameter, you basically learn the update that you want to incorporate into the parameters, right? So this is going to be your modified parameters. So this is the update of the parameter, this is the original parameter, and you update the original parameter with the new updates, right? So you only learn the updates. Clear? So this is essentially global optimization. I mean, one part of global optimization. The third one is local modification, where this is the parameter space, you identify the parameter which is responsible for this knowledge, right? And you only update that parameter. Okay, you see the difference between first and third, right? The first you add a new set of parameters, in the last you essentially update an existing parameter. You locate and update. And now these three categories, you see a lots of methods proposed in last 2-3 years. In today's lecture, we will discuss one of these methods from each of these categories. We discussed GRACE from this category, external memory. We discussed knowledge editor from global optimization category. We discussed ROM from this category, local modification category, and these are very highly cited, well studied papers. Okay, thank you.